Yes, good morning to you all. Welcome back to my online class. This is the second part of the video lesson we started on cylinders and cone. And in the first lesson, we talked about the surface area of a cylinder and its total surface area. We also discussed the volume, and you saw practical examples, and you saw the interesting part where we convert or transformed the net of a cylinder into the cylinder itself and went back from the cylinder back to the net of the cylinder using GeoGebra. So this morning, my focus is going to be on cone. So I want you to pay maximum attention as I run through the lesson notes for the week or for the second part of the first. This is same week of the initial part, the previous part. This is just part two. So it's a cone. This is a solid shape with a vertex above a circular base. A cone has two parts, a circular face and a curved surface. Examples of objects with cone-like shape are funnel, sharpened pencils, ends, the end of a sharpened pencil, snail shell, a mound of rice, etc. So you can see the shape. Here's a cone with the base at the bottom, and here's another cone with the base at the top. All right, so I just gave you two different views of the cone and with the label. So this is the circular surface. Here are the curved surfaces, both cone, and here is the other circular surface. All right, so for the cone, we have the height. It is at the center of the circle. It's coming from the center of the circle to the peak of, that is the apex of the cone. That is the height. I'll call it the altitude. Why? From that same center to the one point of the circumference of the circle is the radius of the cone. All right, so let's look at the net of a cone. When we say net of the cone, oh, this is a beautiful net. See, the net of the cone, the net of a cone, as seen below, is made up of a circle and a sector of a circle. Can you see the sector below? So here's the sector of the cone, and here's the sector of the circle, and here's the circle itself. So by the time we fold this net, it's going to produce a cone. I'm sure you're going to be asking, you're asking already, how is it possible? How can this produce a cone? Now watch out and see how it will produce a cone using the resources GeoGebra. So can you see that? So this is the net at the left hand of this of my screen, and here's the complete cone. Now let's see how this net will produce this figure, the shape you see at the right side of the screen. Watch out, just watch. Can you see what is happening? Are you observing what is happening? The net is producing the cone. Wow, lovely. So now we are opening it up again. You're opening up the cone back to the net. Did you see that? Can you all see that? It's opening up. It has opened it up back to the net. Then it's going back to the cone. I love doing this. I hope you're enjoying what you're seeing. I love GeoGebra. It's a powerful tool. Beautiful. So you can see the net has produced the cone again. Okay, so that is how the net can produce a cone, and that is how. So I believe you understand the net of a cone now. When you see the net of any cone, you understand, you know, oh, this is a net. And if you want to produce any cone, just start up with the net. Start up with something like this, and go ahead and demonstrate. Do what I've demonstrated for you on my screen just now. Now welcome back. So let's look at the formula for surface area of a cone. Now I have a semicircle and a complete cone. Let me quickly explain the concept here. Now I said the sector A, B, excuse me, this is a typographic error. The sector you see here, AXBO, AXBO below with angle theta. Here is angle theta. With angle theta is bent to form the curved surface of a circle, of an open circle with the height h and radius r. All right. So this sector is bent to form this curved surface of an open circle. There's an open circle here. Then it has formed the curved surface area of the curved surface of the cone. Now let's look at how do we deduce the surface area of the cone from this sector. Please pay maximum attention. Now we said length of an arc, or length of arc AXB. Here is arc AXB of the sector is equal to a fraction of the circumference of the circle. Don't forget that this is a circle. If I'm to complete the circle, it will go something like this. All right, can you see that? If we're to complete the circle, it's something like this. So to get the length of this part AXB is just a part or a fraction of the circumference. Therefore, the length is equal to the angle formed at the center, this angle theta, over 360, because the angle at the point is, the whole point is 360, times 2 pi L. All right, 2 pi L. We call this point, this side L. The L is equal to the R. This L is the slant height of the cone. Right, so this slant height of the cone, this height you see here, is the radius of the sector. So that is the angle formed at the center over 360 times 2 pi L. That is equal to theta over 360 times 2 pi L, where the theta, the angle is the obtuse angle AOB. This obtuse angle AOB labeled. So the circumference of cone base is equal to 2 pi R. The base of the cone, here is the base, which is the circle. The circumference of the circle, of course, is 2 pi R. Now, using circumference of the cone base as the length of the arc AXB. Now, the arc we are looking at, all right? So, the arc AXB, we want to now use we want to see the circumference at the length of that arc AXB. But after folding this shape to form the curved surface area of the cone, that will be the length of an arc. Am I making sense here? Therefore, when you do that, when you equate those two things, this arc we've looked at already, the arc we've resolved, we're saying this arc is equal to the circumference of the cone base. Now, by the time you equate those, 2 pi R is equal to theta over 360 times 2 pi L. All right, so dividing through by 2 pi, we have 2 pi R over 2 pi equals theta over 360 times 2 pi L times 2 pi. So 2 pi, you factor out this 2 pi. This, you factor out this. We're left with R equals theta over 360. So here we label this equation as equation 1. Now going forward, also we have curved surface area of cone to be equal to area of sector AXBO, which is equal to theta over 360 times pi R times pi L squared. So this is the area of a sector. Okay. Now when we arrange, we have this theta L times pi L over 360. Just rearrange this equation, this particular formula here, rearrange it to get this. Okay. Now, by very close inspection, you discover that everything what I have here is nothing but equation 1, which is R. So when you substitute, by substitution, this is R equals pi L. So therefore, you can say that the curved surface area of a cone is equal to pi R L. So this curved surface area is equal to pi R L. So everything we've been all through is just to derive this formula. The curved surface area of a cone is equal to pi R L. Please don't forget it. It's very important. Also, the total surface area of a cone is equal to the curved surface area of the cone plus the area of the base circle. So we add the curved surface area pi RL plus the base circle pi R squared, or we can simplify it or factorize to get pi R into L plus R. where r is the radius of the base and l is the slant height. Like I said, so this r here is the radius of this base and l is the slant height of the cone. So if you are given the area of the base and the slant height of the cone, you can calculate the total surface area of the cone. Let's see a practical example. Example says find the area of the curved surface area of the cone with radius 4 centimeters and height 3 centimeters. Give your answer in terms of pi. Solution. You are given r as 4 centimeters, the height h as 3 centimeters, and the slant height is unknown. Okay, so let me quickly draw that a cone here and show you the parts that are given. So we're given the radius as 4 centimeters. We're given the height as 3 centimeters. Don't mind my shape. Now we're supposed to calculate the slant height. Now, by the time I extract the triangle in that cone, you observe that that triangle is a right angled triangle, something like this. Don't mind my shape. 3. So now we need to apply previous knowledge. So in a right angle triangle, how do you solve for an unknown side? Yes, using Pythagoras theorem. That is correct. So this is Pythagoras theorem over here. To solve for the longest side, which is the unknown side right now, slant height, we apply Pythagoras theorem. L squared equals r squared plus h squared. That is equals 4 squared plus 3 squared, which is equal to 16 plus 9, and that is equal to 25. Okay, that is 25. So and when you take the square root of 25, that will be equal to 5 centimeters. It means the slant height is 5 centimeters. Please bear with me, that was the typographic error. So now, but the curved surface area of the cone is pi RL, all right? Pi RL. So that is pi times 4 times 25, and that will give times root 25, and that will be equal to 5 times 4 times 5, and finally that will give 20 pi centimeters squared. So we are solving in terms of pi in this particular instance. 20 pi centimeters squared. So this is the curved surface area of the cone, and here is the slant height of the cone. I hope that was clear enough. All right, so let's continue. And let's see the volume of a cone. And watch, listen to or observe this. See, if we have a cone and a cylinder of same height, just like seen in the picture, and same base diameter as shown by the diagram below. The cone filled with water and transferred or poured into the cylinder. It would be observed that the volume of the cone filled the volume of the cylinder 3 times. So I will need to pour water into this cone 3 times before to fill this cylinder 3 times. So this is a cylinder and a cone with the same base height. Now I'll show you something quickly also on GeoGebra to also further explain my claim right now. All right, so see this to understand my claim. Like I said earlier, that the volume of a cone is 3 times the volume of a cylinder. Oh, sorry, the volume of a cylinder is 3 times the volume of a cone. When you pour water into a cone, you need to fill it 3 times and turn it into the cylinder before it to fill it up. Now, watch what I'm trying to explain here. If you observe here, I have a cylinder by my left and have a cone by the right. The cylinder is blue, the cone is green. You check at the bottom, it states the volume of the cylinder is 11.4, while the volume of cone is 3.8. Now calculate. Divide 11.4 by 3. That is 9. Remember the 2, that is 8. So you can say 3.8. Now when I decide to reduce the height of the shapes, observe what is happening to the volumes. So you can see that the volumes are also reducing as the height is reducing. The volumes is good, their volumes are going down until there is no height and the volume is equal to 0. If I increase the volume, the height, the volumes of those shapes will increase. And as the volume of the cylinder is increasing by three times the volume of the cone, is changing by three times the volume of the cone. Now look at the radius also. As I reduce the radius, they're having same radius. You can see what is happening to the shapes. And when I increase the radius, see what is happening to the shape, okay? Now, finally, to show you, to further explain that the volume of the cylinder is three times the volume of the cone. Now, watch what we have on here. I want to try and move the cone into the cylinder. Observe what is going to happen. Can you see that? So now I've placed the cone inside the cylinder. So you see that the cone actually divides the cylinder into three parts. Now, this first part is this particular part, this empty space by the left, the empty space by the right, and the space occupied by the cone. So you can see this is three of the cone, three of the cone. So this is also a point to explain my claim that the volume of the cone is 1/3 of the volume of the cylinder. Is that taken? All right, now let's go back to our lesson. So having explained that, let's see what follows next. So therefore, the volume of the cone is equal to 1/3 times volume of cylinder with same base and same height. That is equal to 1/3 times base area times height. That is 1/3 by r squared h. Remember that the volume of a cylinder is by r squared h. So while the volume of a cone is just adding a 1/3 to the volume of a cylinder, and that will give you the volume of a cone. I hope that was clear. Good. Example, calculate the volume of a cone with height 6 centimeters and base radius 7 centimeters. Use pi as equal use pi as 22/7. The solution. We are given the height as 6 centimeters, the radius as 7 centimeters, and pi as 22/7. So using volume of a cone as 1/3 by r squared h, we substitute 1/3 times 22/7 times r times r. So this is our r squared. R is times 7 times 7 times 6. And one of these 7 will factor out this. So we left it 22 times 6. Okay. 3 can also cancel 6. We are left with 2. That is 22 times 7 times 2, which is equal to 308 centimeters squared. I hope that was clear enough. Very simple. All you need to do here is understand the formula or memorize the formula and apply. You must know how to apply. You must remember the formula whenever you're asked. So here's our exercise. It says, from also your textbook, New General Mathematics for JSS 2, exercise 19E, number 6, page 174, and exercise 19F, number 2 and 4 of page 176. So this brings us to the end of the lesson for the week. I'm going to post you exercises also or assignments for this particular class, and let's meet again on Friday for our weekly quiz. There are questions. Feel free to post the questions, and do have a wonderful day ahead. Thank you. Have a nice time. Goodbye.